I want to state a few basic facts about the space of square integrable functions on SU2 that we can denote like this. So let me zoom out a little bit. L2 is the space of square integrable functions, and then here I put SU2, just to denote the fact that we are considering functions that are described in terms of a group SU2, and they are square integrable. I want to make a comparison with the square integrable functions on U1. So it's a simpler group which gives rise to the Fourier series expansions. In this case, we consider functions psi of a certain angular variable theta, and this is, for instance, the space of the quantum states of a particle on a circle. We have, for instance, the scalar product of the kind psi, capital Phi, which can be defined as 1 over 2 pi integral from 0 to 2 pi d theta, and then we have psi of theta conjugate phi of theta. Now, the space of these functions carries a representation of the group U of 1, and this group acts simply like this. Psi of theta becomes psi of theta plus alpha. A basis of functions orthogonal with respect to the scalar product is given by the functions psi sub n of theta equal to e to the I n theta with the integer n, so n is an integer. And this is the discrete Fourier transform, basically. These functions here form a complete set because we can construct the Dirac delta of theta in the following fashion: 1 over 2 pi, then we sum over n, e to the I n theta. So you can see that we can construct this delta, and therefore we can construct basically any functions. This is also known as the completeness relation, which is also important in quantum mechanics. Now, we can go to the group SU2, which generalizes what we have just seen. Basically, we have an inner product there as well. We have functions that depend on a certain group, U. This can be thought of as a 2 by 2 complex matrix, and it's such that U dagger U is equal to the identity, or also U dagger is equal to the identity. Then we can define here as well an inner product psi phi that we define as an integral over SU2 in this case, du, and then we have a psi of u star phi of u, something like this. The space of these functions carries a representation of the group SU2, which acts in the following fashion: psi of u goes to psi of lambda inverse u for lambda which belongs to SU2, something like this. The basis of functions which are orthogonal with respect to the scalar product is given by the Wigner matrices. In particular, we can label them as psi j and m of u equal to d j and m of u, where these are the Wigner matrices. This is also known as the Peter-Weyl theorem. Peter-Weyl. Now, also for the SU2 group, we have a completeness formula. In particular, we can construct the Dirac delta of the group as a sum over j. Then we have the dimension of the Wigner matrices to j plus 1. And we have the trace of the Wigner matrix dj of u. So this is a formula that we have already written down in the previous video, and it is just some kind of comparison between the harmonic analysis of SU2 and the harmonic analysis of U1.